Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Okay, so problem number 1. Find the tangent line to the point 1, 1, which is this point right here, in the equation y equals x squared, this equation here, using the circle x squared plus y minus 3 halves quantity squared equals 5 fourths. So here's our circle, x squared plus y minus 3 halves squared equals 5 over 4. So that tells us that our circle is centered at x equals 0, y equals 3 halves. That's this point right here. And we want to evaluate a tangent line at the point 1, 1. Yeah, find the tangent line at that point right there. And so we'll use this circle by constructing a radial line from the center to the point 1, 1, like that. And what's the slope of that radial line? So we'll call it m sub r for radial line. It's going to be equal to 1 minus 3 halves divided by 1 minus 0, which is equal to minus 1 half. So that means we can write the radial line as y sub r is equal to minus 1 half x, that's the slope times x, plus 3 halves, that's the offset. Okay, so the tangent line is perpendicular to this, so it has slope m sub t will be equal to minus 1 over m sub r, which is just equal to minus 1 over minus a half, which is just equal to positive 2. And its center will be at 1, 1, because we want 1, 1 to be our new origin for this line. Otherwise, it's going to pass through 0, 0. And so to get an equation like that, the tangent line is y t equals 2 times x minus 1 plus 1. And that would give us a line passing through this point here. There we go. Something like that. There we are. That's our tangent line. And that is problem number 1. The problem number 2 says, what is the derivative of y equals x squared at x equals 1? Use the results from problem 1 to solve. Well, the derivative is just the slope of the tangent line at that point. So we know that the derivative, this would be problem 1. We're now on problem 2. And since the slope of the tangent line at 1, 1 is m sub t equals 2, then y prime at 1 is equal to 2. Alternatively, we could write this as dy dx at y equals 1 at 1 is equal to 2. All right, problem number 3. Approximate the derivative of the function y equals 2 minus 5 over x at x equals 4. That's this point right there. Using the secant lines. And so I indicate that there are 3 secant lines. The first secant line crosses at x equals 2 and x equals 6. So x equals 2 and x equals 6. So it'd be somewhere here. At x equals 2, it's down here somewhere. So I'll just sketch in the first secant line. Secant, by the way, means the line that cuts. So that's cutting this curve. Let's see how well I can draw a secant line through that. That's not bad. There's that secant line. Yeah, so that's at x equals 2, x equals 6. The second secant line crosses the curve at x equals 3 and x equals 5. And the third secant line crosses the curve at x equals 3.9 and x equals 4.1. Okay, so let's do the secant lines first. So the first secant line is equal to, or the slope rather, so m is equal to y of 6 minus y of 2 divided by 6 minus 2, and that's going to be equal to, plugging in, so we need some more room here, huh? That'll be equal to 2 minus 5 over 6 minus 2 minus 5 over 2 divided by 4, and that's going to be equal to 10 over 6 times 1 over 4, which equals 5 over 12. So there's the first secant line slope. I think you can use that as a template to get the second line, which will have a slope equal to 1/3. And the third secant line, oops, this one will actually run through partially. So at some point in the calculation, you're going to get that it's equal to 10 over 2. Actually, let me show you how to do this one, because this one is a little trickier. So what I'll do is I'll just set it up as before. So m is going to be equal to y of 4.1 minus y of 2.9 divided by 4.1 minus 2.9. And what I'm going to do, so that I don't have to deal with decimals, is I'm going to write this as 2 minus 50 over 41. That's the same thing as 2 minus 5 over 4.1 minus 2 minus 50 over 39 divided by, well, 4.1 minus 3.9 is 0.2, so that's 2 over 10. So I'll write that as 2 over 10. But that is the same thing as 10 over 2 times 31 over 41 minus 28 over 39, which can be written as 5 times 4 times 8 over 41 minus 7 over 39. So you see I factored out a 4 out of this. Right? That's not a 31, that's 32. Sorry, that was dumb. Okay. This is the same thing. 5 times 4 is 20 times, that's 312 minus 287 divided by 1599. And this is the origin of the hint that I gave, which I said we're just going to approximate 1599 by 1600. And so this is the same thing as 20 times 25 over 1600, which is the same thing as 10 times 25 over 800, which is equal to 25 over 80, which is equal to 5 over 16, which is the exact value of the derivative. So I mentioned in the rest of the problem, after calculating the slopes of these secant lines, compare them with the actual value of the derivative at x equals 4, which is 5/16. When calculating, feel free to make a reasonable approximation that 1599 is approximately 1600. Describe the trend you observe in the slopes of the secant lines as they get closer to the point of tangency at x equals 4. So as the interval around x equals 4 tightens, the secant lines get closer to the true value of the tangent line at x equals 4. And you can kind of see that as these tangent lines move in. So here's the first tangent line. The second tangent line is going to be closer. And then the third tangent line, is going to be, pretty close to the actual tangent line. This is the one at x equals 3.9 and x equals 4.1. And that is the trend. If I were to kind of graph, secant divided by tangent, the actual tangent line value, right, where 1 is perfect, then what we see is that this thing kind of closes in on 1. So 5/12 was the first value we got, and then we got 1/3, and then we got 5/16, which is exactly the right value. So that's this point, this point, this point. So you can see as we move closer to that point of interest, x equals 4, the secant lines get closer to the actual tangent line slope. Okay, problem number 4. Calculate the following limits. Note a left limit approaches from the left and the right limit approaches from the right. For example, the limit as x approaches 0 from the left, denoted with a 0 minus sign, means that we start with some negative x value like -2 and make it smaller, or actually bigger, towards 0. So like -2, then -1. So we get closer to 0 coming from the left. So there are 5 parts. 5 parts to this. Part A is pretty straightforward. We want to take the limit as dx approaches 0 for the quantity, what is this? I guess that's an A. No, that's a 9. Can't even read my own writing. 9 times the square root of x plus x dx. So in a problem like this, we can simply imagine substituting in dx for 0, eliminating this term here, leaving us with only 9 square root of x. So I would call that the correct value for that. Let's look at b. b, the limit as x approaches 3 of x minus 3. Well, as x approaches 3, we can imagine just substituting in x equals 3. We get 3 minus 3 is 0. So this limit approaches 0. C, the limit as x approaches 0 from the left of 1 over x. So what does that look like? Well, we need to get a graph of 1 over x. It's going to look something like this. So if this is x, 1 over x goes off to infinity. That way, and on this side, we go in that direction. So if we come from the left, so this is like coming from the left, approaching 0, which is here is the origin, approaching 0 from the left, this goes off towards negative infinity. You can see it going off to negative infinity. So this I would write as minus infinity. D, the limit as x approaches 0 from the right of the same function. Well, here we can see as we approach 0 from the right, we're going this way this time, and you can see that as we approach 0, the functional value is increasing up towards positive infinity. So this one we'll call it plus infinity. And finally E, which is the limit as x approaches 0, not from the left or the right, but from both directions, of 1 over the absolute value of x. Well, what happens then? Well, if we square this, what we're going to end up getting, right, so this was 1 over x. 1 over the absolute value of x is going to look like this. Here's our xy axes. It's going to go up like this. And it's going to go up like this. So from both directions, both from this side, from the positive side, and from the negative side, they both approach positive infinity. All right, number 5, consider the equation x of t is equal to 1/2 at squared plus bt plus c, where t represents time and x represents distance. Calculate x dot and x double dot. Can you think of a suitable relabeling of the coefficients a, b, and c for the case where the distance x is altitude, distance from the ground? Also, can you think of a value for the coefficient a? Finally, what does x dot and x double dot represent physically? Okay, so let's do the derivatives first, right? So x dot, that's just the first time derivative. So we can actually use the rule that we got in the class where we said that d over dt of t to the n is equal to n times t to the n minus 1. We can use this rule and we can apply it to each term one at a time. I don't think I mentioned that in class. You certainly get that in a calculus course, that derivative will be applied over each of these terms one at a time. So I can say that x dot of t will be equal to, well, I first do this term, 1/2 at squared, using this form here. It's going to get me 1/2 times 2a times t. Well, the half and the 2 cancel, so I just get a times t. And now I apply it for the second term, plus b times t. Well, t, that's t to the first power, right? So I get 1. So b times 1, which is just b, and t to the 0, but t to the 0 is just 1. And then the last term. Well, you recall we also had a rule from the lesson where the derivative of a constant is 0, right? That makes perfect sense because if I have a function that's of constant value, right, and I were to ask, what is the slope of the tangent line on this curve? Well, it's 0. It's just a flat horizontal line, so it is 0. So we get nothing after that. So that's x dot. What about x double dot? Well, we can just do the same thing again. We apply the derivative not to the first equation, x of t, but to the equation x dot of t. And so a times t, well, t is to the first power, so that gives me a times 1 times t to the 0, and t to the 0 is just 1, so it just leaves me with a. B is a constant this time, which makes the derivative 0. So x double dot of t is just a. And as far as the reassignment of values, so what this should trigger in your mind, I guess, is you should recognize this original equation as something we saw in kinematics that talked about the displacement in terms of an acceleration and a velocity. So we could relabel A to be equal to g. That's the acceleration due to gravity. So that's 9.8 meters per second squared. We could let b, the coefficient up here, b, what does that give us? Well, if we look at the second equation, x dot of t, when t is equal to 0, x dot of t is equal to b. So that's really just our initial velocity, right? Similarly, if I look at the equation x of t at t equals 0, this term goes away, this term goes away, I'm left with just c. So what do we call that? We call that x naught, right? That's our initial position. So we could replace c with x naught. And then we interpret, of course, x dot. This is just the velocity equation. And x double dot is just the acceleration equation. And that's pretty much all I was looking for in that problem. Okay, I'm going to do 6, 7, 8, and 9 kind of all together because it's a variation of the same theme. The first one asks us to simply sketch a graph of y prime. Sketch a graph of y prime for this curve here. So if this is f, right, then what does f prime look like? I guess we could call it f prime, not y prime. Well, we can imagine taking our tangent line, and sometimes you can do this with a ruler. If you imagine what your tangent line looks like at each of these spots, right, it's going like this, it's falling up like this. You can see at each of these points along here, it's increasing like that. And so we can imagine that what this is doing is that the tangent line is going to, on this side anyways, it's going to be a function that looks something like this. So you can verify that. Well, I guess you can't because I can give you a functional form. That's the idea, though. So that's what we're looking for in that. It doesn't need to necessarily match up here. I guess it could be more like this. There we go, something like that. Number 7, which got a little scratched out. What does number 7 say? It says, number 7 says, locate the minimum value for the function below. What is the value of the derivative at that point? Okay, so here's f. It's asking for the minimum value. Obviously, it's this point right here, right? That's the minimum value. And so if we think, what does the tangent line look like at that point, right? It's traveling along here. It's negative at first, and now it becomes 0 at this point, and then it starts to become positive again. If we go from being negative sloped to positive slope, we must have gone through 0 in between. And so the tangent line at this point is just a flat line, flat horizontal line, whose slope is 0, which means that f prime, and I guess we call, what do we label it? I don't know. We'll just call it f prime at min is equal to 0. Number 8 is a similar question. It says locate the maximum value for the function below. What is the value of the derivative at that point? So here the maximum value is obviously this point at the top. And so we would do a similar thing with our tangent lines as we went from a positive slope and then we became a negative slope over here, right? In between we must have been 0. We're 0 right here at this maximum. So here the tangent line also has a slope of 0, which means that f prime max equals 0. I don't know why people keep messaging me. Sorry about that. And then finally, number 9 says, find the point in the function below where the derivative is equal to 0. Why do you think this point is 0? So here we don't have a clear minimum or maximum. You can see that it's kind of going off in both directions, but you see that as we start out on the left, we have a positive slope. Oh my God, what is the big emergency? Okay. So the idea is that as you approach this point right here, call it x naught, it's this point right there. So you approach this from the left, the derivative is decreasing, right? Because we're decreasing, right? It's not the same as before where we had a negative slope and then after passing some point we had a positive slope. Here we're just simply, the slope is decreasing, right? And then after you pass this point x naught, the derivative begins to increase again, okay? And so, yeah, I'm not sure I agree with the logic of this one. It must be some 0 somewhere in between. I suppose you could start out with a steep slope, you could decrease and not quite go to 0, and then start increasing again. But I think what I was looking for in this one is what we typically call an inflection point. But in an inflection point, really what you have is you have kind of a reversal of the curvatures, right? So over here, it would look like this. So on this side, we're decreasing our slope as we approach. And then we change directions again. Still positive slope. It was never a negative slope anywhere. But this kind of act of changing back, right, this inflection point is another place where the derivative, f prime, let's call it inflection, can be equal to 0. Okay, problem number 10. Problem number 10 says if the function f is a diagonal line and f dot, right, or x dot, whatever, is a horizontal line, then what can you say about f double dot, which I wrote as x double dot here? So the answer, I guess, quite simply is f, I write it the same way, x double dot is equal to 0. Why? Well, because the slope of x dot is horizontal, and the slope of a horizontal line is 0. So if I were to let g equal, I'll write f dot this time, and that's equal to a constant, right? Some constant. Then g dot, which is equal to d over dx of a constant, is that right time? Sorry. D over dt of a constant is equal to 0. So g dot, which equals f double dot, is equal to 0 as well. It all hinges on x dot being a constant, therefore x double dot is 0. This is all to kind of build up your familiarity with these graphs of things like position, velocity, and acceleration. And you'll get more of that as you spend more time with physics. But that's really all these last several exercises were designed for. 5 through 10 was to familiarize you with the ideas that we have relating the position, velocity, and acceleration curves to each other through derivatives and integrals. Okay, problems 11, 12, and 13 really apply to lesson 96 as far as integration goes. But let's start with number 11. It says you can fit 5 18-degree right triangles into one of the 4 quadrants in the circle to your left. The area of the circle is given by a equals pi r squared. If we let r be equal to 31, then the area is a equals pi times 31 squared, which is 3019 approximately. Use the 18-degree right triangle with legs of length 31 and 10 to approximate the area of the circle. Okay, so here's the circle. These are the 4 quadrants I'm talking about. So you can see that you can fit 5 18-degree triangles, 1, 2, 3, 4, 5, into one of these quadrants. That's a 90-degree segment. So where's my pen? So what we can do, right, so the legs of it was, this is the radius of the circle, and so this leg, and this leg, and this leg, and this leg are 31 in length. These legs are 10 in length, and the tangent of 10 over 31 is approximately 18 degrees. It's not exact. But let's see what we can do with that. So we'll just simply write that the area, right, is going to be equal to 4. Why 4? Because there are 4 quadrants. So whatever area I get when I add up the area of these little triangles, I need 4 of them because there's 1, 2, 3, 4 quadrants to fill to make the circle, times 5. Why 5? Because that is the number of 18-degree triangles that we can fit into one quadrant. Finally, times 1/2. Why? Because we're going to use the area of a triangle formula. It begins with 1/2 base times height. And so our base will be 31, the radius. Right? So this is the base. And the height or altitude is 10. And if I multiply all that together, I get 3,100, which is pretty close to 3019. If you divided it up into more triangles, so cut these in half, so you had a 9-degree triangle, you'd be able to fit 10 triangles in each quadrant. However, the side lengths would be a little bit different, right? You have to change. It wouldn't just be half of 10 is 5. It'd be a little bit less in order to make any headway with that. Okay, problem number 12 So it says, in lecture 96, I asked you to do the algebra to show that m minus 1 choose 0 plus 4 times m minus 1 choose 1 plus 5 times m minus 1 choose 2 plus 2 m minus 1 choose 3 is equal to 1/3 m cubed plus 1/2 m squared plus 1/6 m. Well, it's really just a lot of algebra, right? I'm not going to do all of it, but m minus 1 choose 0. Of course, that's going to give us 1 because we would have m minus 1 factorial divided by 0 factorial times m minus 1 minus 0 factorial. So the m minus 1 factorial in the numerator and the denominator, we just cancel out. We just get 1. So there's a 1. And then we get 4 times, this one would be m minus 1 is all that would stick around after using the n choose k formula. If you forget the n choose k formula, n choose k is equal to n factorial divided by k factorial times n minus k factorial. So in our case, we're doing, I'll just do 1 just in case you don't get it. In our case, we're doing m minus 1. I'll do the next term here. 5 times m minus 1 choose 2. So m minus 1 choose 2 is going to be m minus 1 factorial divided by 2 factorial times m minus 1 minus 2. Well, m minus 1 minus 2 is just m minus 3, right? But that whole thing is factorial. If I start writing this out, I would have m minus 1 times m minus 2 times m minus 3 factorial. Just keep on going. Divided by 2 factorial times m minus 3 factorial. You see this m minus 3 factorial completely cancels this m minus 3 factorial. So we're just left with m minus 1 times m minus 2 all divided by 2. And that's exactly what we get in the second term. So we would get plus 5 halves, just the 5. That's going to be m squared minus 3m plus 2. And then the next term is this 2m minus 1 factorial over 3 factorial m minus 4 factorial. So what is that going to give me? That's the hardest term, I guess. So you're going to get a 1/3. And if we multiply this out, this m minus 1 times m minus 2 times m minus 3, we're going to get m cubed minus 3m squared plus 2m minus 3m squared plus 9m minus 6 here at the end. And just start arranging. We've only got one m cubed term in here, so we can go ahead and write that down. So that's 1/3 m cubed. That's from here. Now let's look at our squared terms. So we'll pull out the half. And so that'll leave us with 5m squared minus 4m squared, which I got from combining these terms over here. Okay, and then finally, plus, we'll pull out a 1/6 out of the m terms. 1/6 times, that'd be 24m minus 45m plus 22m. And you can see that right there, that 24 plus 22 is going to give you 46, and 46 minus 45 is just going to give you 1. And so we're left with 1/3 m cubed plus 1/2 m squared, because 5 minus 4 is 1, plus 1/6 times m. And that's the formula we were looking for. The algebra sucks. Half the time when I do these, I get the wrong answer. So you have to do it a few times and use the one you think is the best fit, or the one that you kind of expected. Okay, that's number 12. Okay, the bonus question, number 13, we want to show that we want to basically derive the area formula using the small angle approximation that the tangent of theta is approximately theta. This is actually pretty straightforward. It's pretty easy to do. You know, if Archimedes had trigonometry, right, he would have wouldn't have to go to all the trouble he went to with his method of exhaustion proof for the area of a circle or sphere. I think he did the area of a sphere. Anyway, or volume of a sphere. That was probably the tough one, but maybe he did area of a circle. I don't know. This is straightforward, though. Let's see. How do we do it? Well, we're going to say that the area, we're going to go back to that problem number 11 that we did, where we were breaking the circle up into, quadrants that contain triangles, right? And so I want to basically use the same format there. So I'm going to say that the area is equal to, I'm going to divide up the 2 pi radians inside the circle, right? Because one revolution inside the circle is 2 pi radians. And I'm going to divide that by my theta, my step size, and that's going to give me the number of triangles that I can fit inside of this circle. And then we'll multiply that times 1/2. The triangle base is going to be r, and the triangle height is just r times the tangent of theta. So this is the triangle height for each of these triangles that we have here, and this is the base. So this is just our formula, right? So we're going to divide up the entire area of the circle into some number of triangles. So if we used, 18 degrees again, we'd have 20 triangles, right, to fill the whole circle. And then we choose our base, r, that's just the radius of our circle, right? And we can, if we know the radius of our circle and we know the angle theta, then we know this distance here, because if this is r, this is just r times the tangent of theta. And so now we want to use the small angle approximation. So if we replace tangent of theta with r, what do we get? Well, this becomes just theta, right? This becomes r squared. I'll write it down here. So we're going to get a is equal to, we'll say approximately, since it's an approximation, we have 2 pi over theta, but we've got a theta up here. So these will cancel. This and this will cancel. And so we just have 2 pi. But why 2 pi? Well, we've got a half right here. Let's cancel this 2 and this 2 in the denominator. So we're now just left with pi times r. Well, that's just r squared, and we're done.